All right, let's just dive right into this. Welcome to an explainer that's honestly going to change how you look at the invisible universe shifting around you every single day. Today, we are demystifying chemical reactions and equations. We're going to take what often feels like complex, abstract science and break it down into a clear, structured visual journey. And by the end of this, you'll literally be able to read the secret mathematical language of the universe.
So, we're kicking things off with a pretty simple mystery. What exactly happens when you leave milk out on a hot summer day? Or, when grapes ferment? Or when an iron nail is left outside and begins to rust? These aren't just random occurrences. In all these situations, the initial substance fundamentally changes its nature and identity. And when a change in identity happens, it means a chemical reaction has taken place. The matter itself has rearranged.
Here is our roadmap for today. First, recognizing reactions. Second, writing equations. Third, balancing the scales. Fourth, types of reactions. Fifth, energy exchange. And finally, everyday chemistry.
Okay, section 1, recognizing reactions.
In our detective phase here, we really need to know what physical clues to look for at the scene of a reaction. How do we actually know that bonds between atoms are breaking and reforming right in front of our eyes? Well, you might see a sudden change in state, or a dramatic change in color, like copper turning black when it's heated in the air. You might witness the evolution of a gas, which usually just looks like vigorous bubbling. You might see the formation of a precipitate, which is when a solid suddenly drops out of two mixed liquids. Or you might physically feel a sudden change in temperature. And this brilliantly illustrates the point. When you mix zinc granules with dilute sulfuric or hydrochloric acid, it visually proves a reaction is happening right then and there. You get this rapid evolution of hydrogen gas, you can see those bubbles fizzing up, and if you were to actually touch that flask, you'd feel a distinct sudden spike in temperature.
Moving on to section 2, writing chemical equations.
Okay, now that we've found our clues, it's time to document them like true scientists. We need a way to communicate what we're seeing efficiently. Notice how a pretty clunky word equation gets translated into a sleek, mathematical chemical equation. If we burn magnesium in the air, we could write out magnesium plus oxygen becomes magnesium oxide, but that's incredibly long. Instead, we use chemical formulas. We put our reactants, magnesium and oxygen, on the left side, we draw an arrow to show the direction of the change, and we put our final product, magnesium oxide, on the right. So Mg plus O2, arrow, MgO. It's precise, it's universal, and it's way faster to write.
Section 3, balancing the scales.
Let's put on our accountant hats for a second. This is basically the cosmic ledger, the law of conservation of mass. It states that matter simply cannot be created or destroyed in a chemical reaction. You can't magically conjure up new atoms, and you can't make existing atoms vanish into thin air. You can only rearrange them. Because of this, the total mass of the elements in the products absolutely must equal the mass of the elements in the reactants. To enforce this law, we've got to balance our equations. We use what's called the hit and trial method. Now, I know that sounds a bit like a messy car crash, but it's actually a highly methodical, step-by-step process of trial and error to make sure both sides match perfectly. First, you draw boxes around your formulas, because you can never change the formula itself, only the amount of it. Then you count the atoms of each element on the left-hand side and the right-hand side. Next, you adjust the whole number coefficients in front of those boxes until the numbers match. And finally, you do a quick check to make sure everything's balanced. Let's actually see that process in action. In the unbalanced equation for iron reacting with water, we've got one iron atom on the left, but 3 on the right. No way! That completely violates the laws of physics. So, by using our hit and trial method, we add coefficients. In the balanced version, adding a 3 in front of the iron, a 4 in front of the water, and a 4 in front of the hydrogen gas brings our iron, hydrogen, and oxygen atoms into perfect mathematical harmonies on both sides of the arrow. We can also upgrade these balanced equations to give us even more context. By adding these tiny state symbols in parentheses, we make our documentation incredibly precise. We use an S for solid, L for liquid, G for gas, and AQ for an aqueous solution, which just means it's dissolved in water. We can even use an upward arrow to quickly show a gas was evolved, or a downward arrow to show a solid precipitate dropped out of the liquid. Section 4, types of chemical reactions. With our balancing skills totally locked in, let's look at the grand categorization of all the chemical suspects we might encounter out in the wild. Chemists classify reactions into 5 fundamental formats that dictate exactly how matter interacts. We've got combination, decomposition, displacement, double displacement, and oxidation reduction, which we usually just call redox. Let's break down exactly how these work right now. The first two are exact opposites of each other. A combination reaction is exactly what it sounds like, when two or more reactants combine to build a single larger product. For example, hydrogen and oxygen combining to form water. On the flip side, a decomposition reaction is when a single larger molecule splits apart into simpler substances, and this usually requires an input of energy like heat. Here you can see calcium carbonate breaking down into calcium oxide and carbon dioxide. Next up, we have the displacements. Think of a displacement reaction like a simple dance partner swap. A more reactive element literally cuts in and kicks a less reactive element right out of its compound. See how zinc kicks copper out of the copper sulfate? Zinc takes the sulfate and copper is left sitting all alone. Double displacement, on the other hand, is a mutual exchange of ions between two entirely different compounds. They simply swap partners, which often results in a solid precipitate, kind of like the barium sulfate you see forming on the right. Finally, we have redox reactions, which deal with the transfer of oxygen or hydrogen. Oxidation is when a substance gains oxygen or loses hydrogen. Reduction is the exact opposite, losing oxygen or gaining hydrogen. But here is the real trick. They're just two sides of the same chemical coin. They literally always happen simultaneously. If one substance is being oxidized, it is stealing that oxygen from another substance, which is simultaneously being reduced. Section 5. Energy exchange. We really can't talk about matter rearranging without talking about the invisible currency that funds the whole shebang: energy. Reactions don't just happen in a vacuum. They interact heavily with the temperature of their environment. Reactions either blast heat out into the world, which we call exothermic, think of a massive explosion, or even just the heat given off in concrete sets. Or they selfishly pull heat in from their surroundings to fuel the reaction, which we call endothermic. Melting ice, evaporation, or a plant absorbing sunlight for photosynthesis are all classic endothermic processes. And that brings us to Section 6, Everyday Chemistry. Let's look at how all this builds the world you walk through every single day, completely outside of a laboratory. Because chemistry isn't just happening in test tubes. That rusted bike chain you accidentally left out in the rain, it's falling victim to a slow, relentless redox reaction called corrosion, where the metal is gradually destroyed by moisture and acids. And that half-empty bag of potato chips sitting on your counter? The fats and oils inside actively want to oxidize, which changes their smell and taste, a gross process called rancidity. Fun fact, the food industry actually fights this by flushing those chip bags with nitrogen gas to slow down the oxidation process. And honestly, it goes even deeper than that. As you're sitting here watching this explainer, you are a walking, breathing chemical reactor. Respiration itself is an exothermic chemical process where your cells are constantly breaking down glucose to release energy. So look closely at the world today. From the food digesting in your stomach to the rust forming on an old car, absolutely nothing is truly static. It's all just atoms, constantly rearranging themselves. So I'll leave you with this. What other invisible transformations are happening right around you right now? Keep your eyes open, and thanks so much for joining me on this explainer.